In this research we identify and qualitatively describe the hydration layer which is confined between the mechanically exfoliated graphene and an insulating hydrophilic substrate, namely calcium fluoride. Graphene is exfoliated under ambient conditions, applying the well-known Scotch tape method. Calcium fluoride is cleaved under ambient conditions as well, resulting in a calcium fluoride 111 surface. After exfoliation, we inspect the flakes by help of an optical microscope and characterize their thickness with the help of Raman spectroscopy using the G and 2D bands. After preparation, the sample is transported into our ultra-high vacuum setup and transferred under the scan head of our non-contact atomic force microscope. The non-contact atomic force microscope is a special mode of the atomic force microscope, where the cantilever is oscillated at its resonant frequency with an amplitude of a few nanometers. Together with the topography, we record the surface charges with help of Kelvin probe force microscope. The resulting surface potential image, shown in C, enables us to discriminate between the different graphene layer thicknesses. The corresponding topography in A shows a thick water layer underneath the graphene. To understand this water layer, we have to go back to the preparation method. As soon as we cleave hydrophilic calcium fluoride in ambient, water molecules from the ambient start absorbing onto the calcium fluoride 111 surface. When we then exfoliate the graphene layer onto it, a submonolayer coverage of water is confined by the graphene layer. Transport of water from the calcium fluoride surface underneath the graphene results due to capillary forces and explains the obtained images. Annealing results in a decay of the confined thick water film, leaving a thin hydration layer with different height levels. To understand the two different height levels present in the rectangle, we plot the corresponding height distribution. The lowest peak found corresponds to water-free domains, surrounded by the first hydration layer. Imaging several different flakes shows the trend that the number of domains decreases as a function of temperature, while the average size of water-free domains increases, resulting in two-dimensional Oswald ripening of the water-free domains. In an attempt to further increase the water-free domains, we anneal to 750 Kelvin, resulting in water vapor-filled nanoblisters for thinner graphene sheets and ruptured graphene for thicker graphene sheets. Upon cooling, the water vapor condenses into liquid-filled nanoblisters, from which we can estimate the adhesion energy for graphene and calcium fluoride 111 by measuring its dimensions. This value is on the high side, and it should therefore be easy to transfer graphene from, for instance, a PDMS stamp onto a calcium fluoride 111 surface. The nanoblisters also provide a conceptual basis for a graphene nanosystem for storage and release of chemicals in aqueous environments.